is the method I mentioned last time. And actually, after the class, I realized that I said something wrong about how to find the pole in the input, but it's a good exercise, good mistake that you can learn from me. But first of all, we figure out what is the path from input to output. And then we find out how many nodes we have along this path. We say this is node 1, this is node 2, so I should have 2 poles. For each of the pole, and before that, I definitely need to ground all the independent source. And because of this, I'm going to ground the V-in also, right? And then, how about let's start with pole 2, which I did not make mistake of. Start with pole 2. And what do? We pretend we are the electron, we stand here. And then we ask ourselves, what are the paths for this given circuit that I can go to the ground through a resistor? So I come here, I see CL. I know this is not a resistor. I will ignore it. I should ignore it as if it is not there. Like I'm saying, what are the what are the stairs that will bring me to the ground floor from the first floor, right? I see the elevator, I say I don't recognize it, I only see these stairs. And then you say that, well, I can go up through RD to the ground because it's AC ground, not right? So VDD is AC ground. And I say I also can go through the transistor M1. If you say M1 has no channel length modulation, then it's infinity, right? Otherwise, you just parallel R01, then I'm done with this. Now, how about the capacitor that will bring me to the ground? Then again, from node 2, I go to RD, I say, no, this is a stair. This is not capacitor. I'm looking for elevator, right? What do? I ignore it, right? It's just like I open circuit, or I erase it in this process. And I look at the transistor, also a resistive path for me, so I ignore it. Then I only see CL, right? So the pole equals to 1 over RC, which is CL times RD parallel R01. I got the first pole of this circuit. Is this okay? That's what we did last time, right? Then what did I do wrong last time? Then I go to node 1. And then I say, okay, first I want to find the resistive path that will bring me to the ground. And we correctly say that the path that will bring me to the ground is what? Resistive path. In this case, when I stand here. No, I'm standing at this point, right? This is the node, right? Yeah, just this line, right? And what is the resistance? 0. And then the mistake I make is, what is the capacitor that will bring me to the ground? Okay, last time I said infinity because I got confused by this curve. But as I just said, when I'm looking for the capacitive path, I will ignore all the resistive path, right? So yes, this is shorter because of the methodology, but now I'm only looking for the capacitive path. So it is as if it is open. Or I should not consider that this is always at 0, right? This is not the way for me to determine whether I have a capacitor or not. I just stand here. What I can do, I can remove this, that will be clearer. Then what is the capacitor that will bring me to the ground? Is 0, right? Not infinity. Yeah. You will, but not now. Now, so he has a very good question. How about the CGS, all this thing? In this case, we're assuming we operate at lower frequency, so those are too small to consider. Later, next class, we will consider those. Yeah, good question. So, yeah, so can we know what?
You know they're there.
You know they're there, right? Yeah, I still give you 0 point. It's okay. In the exam, you have the freedom not to answer. Okay. You can answer, say, I think your question is wrong. We're working at low frequency. But
10 terahertz.
okay. Yeah, so because of this, the C should be 0, not infinity, right? So then, then the pole here equals to 0 times 0, 1 over, so it's infinity, right? So again, we don't have the pole, it's yet infinite frequency, okay? Yeah, so I hope that this is a good mistake to make, right? So you won't get confused next time when you see this. Any questions? Okay, if no, then we'll start working on some more complicated example, but it's not difficult. For this circuit, right, I want to know what are the poles of this circuit. So we follow what we need to do, start with input and go to output. So I have a path like this. Then how many nodes do we have? Now, some of you say 3, right? Because I will start with this one, 1, 2, and 3, right? But because of our experience, we know that if I try to have a node here, this is going to be connected to ground anyway. So, and this is just short everything, right? So we will not consider this because this is just because it's ideal. So there's no additional pole induced by that node, right? So from now on, we will just ignore the V in, anything associated with the V in directly, okay? So we do have, what is the second step, however? After I find out the path, I identify the node. What is the second step? Short that. Short the independent source, okay? And of course, if you have current, you open it, right? And then we find that we only have 2 nodes. So we start with node 1. What do? I stand here as an electron, right? It really, I mean, just be very careful, right, in the exam. Follow step by step, don't jump. Don't mess up. So I stand at this point. What is the resistor that will bring me to the ground? Yeah, very clear. This is easy. Yeah, I see Rs. How about what is the capacitor that will bring me to the ground? C in. Unless you say, how about CGS? That will be later, right? So this is completely open. So done. The first pole, P1 equals to 1 over Rs C in. That's it. Okay, so you see very fast, I find the pole. You don't need to solve KCL, KVL. How about the pole due to the second node? So this one requires some careful thinking. The answer probably is the same, but you need to have a careful thinking, right? So I stand here. So my first question is, what is the resistor that will bring me to the ground? It's an RD parallel R01, which is correct, but however, I want to challenge you. Why looking down is R01? Yeah, it's parallel resistor to RD, but but why this is R01 when I look into the drain? Why? Because of channel length modulation, because you're looking into the drain, right? But if you are super careful, you will ask yourself, why I can say that? That is because before we already done the KCL, KVL exercise, and we know that if the source and gates are both grounded, then this is R0. If the gate is not grounded, the source is not grounded, it should not be R0, right? Do you remember this? Right? We got this, it's just because we ground gate and source and solve KCL and KVL on the small signal. Then we get R0, right? But I do not see this is directly grounded. Can you argue that this is grounded? Very good. Because he said the V in is grounded, then this is open, then this has to be grounded, right? So you are right, but I do want to challenge you to think deeper, right? To prove that this is the case, right? Say again? This is for P1, but we are talking about for P2. When I look into the drain of M1, what is the impedance? you say this is R01. But R01 is only correct if the source and the gates are grounded. Then you can say that looking into the drain is R01. If this is not grounded, for example, I have for example, right? It's very easy to just another example. What is the input impedance of this one? I'm looking into the drain also. Isn't that is the drain parallel the gate is based on very naive and wrong thinking? Isn't that then this will be R0 parallel infinity? No, what is the impedance? Huh? No, input is not grounded here, connected to drain. What is the input impedance? What type of? Yes, diode connector, right? So this is 1/GM. Here, just to show you that looking into the drain doesn't mean that the impedance is RO. It really depends on the gate bias. If the gate is grounded, yes, it's RO. If it is not, for example, I connected to drain, or through some resistor, I connected to the drain, it won't be RO, right? If it connected to the drain directly, it's 1/GM, right? Because diode connected. Make sense? And that's why I'm challenging him. I say, can you argue that this is actually grounded? And then you guys told me, yeah, because this is grounded, this is open, then this need to be grounded. Otherwise, if this is not grounded, you keep having current. The current cannot go anywhere, right? Is this okay? So this must be grounded, right? The current cannot go through here neither, because if this is high potential, this current will go this direction, this will go this direction. It violates the KCL. The only possibility is this is grounded. Because this is grounded, therefore I dare to say that looking down is RO. That's what I want to say. Is that okay? How about the C from CL? Yeah. I mean, node 2, right? We're talking about the green one. So the P2 is easy again, is CL times RD parallel R01. And that's it. You already found the two poles of this complicated circuit, right? In a few minutes, or even 1 minute if you are familiar with this. Okay, any questions? In this, we cannot find zero using this method. Yeah. Okay, let's look at another example, but this time use no channel length modulation to make it easier. Again, what do we follow? The path from V in to V out, very good. And then the second thing, we will ground the independence node. Okay, so how many nodes do we have in this case? Yeah, so because of the way I draw it, you hit VB, right? But the curve actually go through the channel, right? So we don't need to do VB in this case. Yeah. Yeah, and I forgot to ground VB. Okay, so we still have two major nodes, right? In this case. Okay, so let's start with 1. So I stand here as an electron. I ask myself, what is the resistor that will bring me to the ground? Let's start with capacitor. What is the capacitor that can bring me to ground from node 1? C in, right? I only see C in for what I draw here. Agree, everyone? How about the resistor that can bring me to the ground? RS. So let's say if there's fire, you are only on the 3rd floor, right? And I say, oh, RS, you cannot go through. I'm sure you will go around to really find is there another stair that can bring you to the ground. So I keep running RS no. Oh, C in no, elevator, I cannot take it when there's fire. And then where are you going to go? Yeah? I still have a path that will bring me to the ground. This is VDD is AC ground, right? a resistive path. And someone already gave me the answer. What is the? So someone say 1 over Gm. But why is that? Why this is 1 over Gm? No CLM is one thing, but what type of, yeah, okay. So he said gate is grounded, no CLM, so it's 1 over Gm. And this is like the input impedance of a common gate amplifier, or it is the, yeah, input impedance of a common gate amplifier. Do you see that? That's what you learn in the first part of this class, right? That's why you need to be very familiar with what we learned earlier. So while I'm saying that we emphasize on the new materials, but if you don't understand the old materials, you won't be able to answer this question. So is this clear to everyone? Looking up here is 1 over Gm. In principle, you don't know that. You will try to solve the small signal model, apply a voltage source, measure the current, and V over I is the input impedance, right? But then you realize that looking up is just like looking into the input port of a common gate amplifier. And we already solved that using KCL, KVL. I know that this is 1 over Gm, right? When there's no channel length modulation. And because of this is RS parallel 1 over Gm1. Anyone has question about this?
Why are we stopping at 1 over Gm?
So he's saying that 1 over Gm1 is the impedance from here to node 2. Is this correct? How did we get 1 over Gm? So basically he's asking why is not 1 over Gm plus RD? You did that in assignment 3 or something already, right? But why we get 1 over Gm? Can you tell me? Did I just came out and said because I'm professor, that is 1 over Gm? Or Rasavi say that? How do we get that? We really prove it by using KCL, KVL, right? We really drew a circuit, the small signal circuit, right? We apply V and then measure I. Wow, this is difficult to see. Right? We solve the KCL, KVL, and we found out that V over I equal to 1 over Gm. Right? Maybe you forgot that, but it's not because I just gave you the equation. We really solve it, right? So you may still feel uncomfortable. What? The RD has no effect? But that is what we got from the math. It has no effect when there's no channel length modulation, right? And you did this in your assignment also. You have a few of the impedance, assignment 3, looking into the source. You use this equation in your assignment, right? So this is some pitfall, even myself always fall in, right? So yeah, so it's good you ask this question. Because I can tell you many students just look at this source and think it's 1 over Gm. But it's not always the case 1 over Gm. The reason looking up is 1 over Gm is first, the gate is grounded. If the gate is not grounded, not 1 over Gm again. You need to solve from scratch. Okay? So this is 1 over Gm instead of RD plus 1 over Gm. Okay? So what is the pole? Pole of first one equal to C in RS parallel 1 over Gm. Okay. How about the second pole? What is the C? C is easier. Let's start with C. Is CL, right? Because you stand there, it is CL. How about the R? What are the resistive path that can bring me to the ground from node 2? He said RD parallel with something. Probably you're saying looking down, right? But looking down, what is the impedance now? Okay. Very good. One say infinite because there's no CLM. We're looking into the drain this time, not the source. Again, the transistor looking from both directions, they're different in small signal because it's an active element. And we use this voltage control current source in the small signal, and we solve a difficult KCL, KVL, and we found that indeed going into the source is different from looking into the drain. Although in DC perspective, they should be symmetric, right? Because of the saturation, we are in the saturation regime. So when you look down, this is actually not 1 over GM, but is it just R0? Can I say it's R0? Again, when can we say the drain impedance is R0? When there is CLM, and how should we bias the transistor to say it is 0? The saturation, but how about this? I just discussed. Gate and source need to be grounded. Is the gate grounded? Is the source grounded? No, right? Because it's connected through a resistor to the ground. So when you look down, what type of impedance you are seeing? I mean, from this point. Do not tell me it is R0 plus RS, okay? What should that be? No, look down from here. We are looking into the drain. So that's why now you need to step back. What type of amplifier you have seen before? When you look into the drain, the source is connected through a resistor to the ground. What type of amplifier is that? Source with degeneration. And what is the impedance when you look into the output port? You may forget the equation, but it is not R0 plus RS, right? It is R0 times 1 plus GM RS plus RS. Yeah. It's okay you forgot the equation, but you definitely need to alert yourself, oh, this is not just a common source. Right? So you need to keep practicing this. Okay? Is it clear that this looks like a common source with degeneration? Right? This is VB. And this is RS. I ignore the capacitor. And what we are looking now is this, right? So this is common source with degeneration output impedance, which is R0 times 1 plus GM RS plus RS, or approximately R0 GM RS. Okay? Okay, so that's a good review. But because there's no channel length modulation, this R is going to be infinity. So this is infinity. So P2 is EC 1 over CL RD. Okay, any questions? Yeah, very good. Right? The only thing I require you to do is that you keep challenging yourself when you come up with a solution, particularly easy solution. Okay.